All right, to go along with our graphing 2x2 systems notes that we looked at in the previous video, today we're going to look at solving 2x2 systems using a couple different methods. So just a reminder, when you graph a system, the solution you get is the same as when you are solving a system algebraically. So the solution to a system is still the point where the lines intersect. And the reason I want to emphasize that is to remember that we're looking for two values, right? X and Y, because we're looking for a point. Now the first method we'll look at is called substitution. And that word substitute means to replace something with something else. And so that's the kind of the basics of the idea of substitution. So in our first system here, we have negative 2x minus y equals 6 and y equals 4. And so because we have an equation where y is equal to something, right, this second equation is already solved for y, we can take that value 4 and put it into the other equation for y. We can substitute it in instead of y, and then we can solve. So negative 2x minus, but instead of y, I'm going to put 4 equals 6. And now we just have a two-step equation. So plus 4 divided by negative 2. And we know that x is negative 5. And since we already know what y is from the setup for the problem, we know the solution is negative 5, 4. Now, they won't always be that easy. For example, example B here, we have y equals negative 4x plus 10 and negative 2x minus y equals negative 6. Now, this is what you want to realize is that substitution is a pretty easy method if one of your equations is already solved for one of your variables here. So this one already has a y equals something. And so it's pretty simple to then substitute in that expression or the numbers we saw in the previous example for that variable. It gets a little more, I don't know if I want to say difficult, but it's definitely more work if you have to solve for x or y first. Anyway, let's substitute this in. We've got negative 2x minus, but then instead of y, I'm going to put this entire thing, negative 4x plus 10, and that equals negative 6. So notice I didn't change the equation. I just replaced this y with this entire expression. And now we can solve. So first we'll distribute the negative 1 here. So negative 2x plus 4x minus 10 equals negative 6. We can combine some like terms. We'll also add 10 to both sides. So we've got 2x equals 4, which means x equals 2 when you divide by 2. So now we can take our value for x equals 2, and since we know that y equals negative 4x plus 10, we can substitute again and put 2 in for x, and now solve this one. So negative 4 times 2 is negative 8 plus 10, which is 2. So now our solution here is 2, 2. And it's always a good idea to just double check your answers by putting in 2 for x and 2 for y in both of your equations, just to double check that it works. And it does in this case. If you try that in both, you get a balanced equal equation. And that's always a good idea to do no matter what equation or system you're solving. But moving right along to example C. Again, this is really well set up for substitution because you have this expression that is already set equal to one of your variables. It says y equals negative 2x plus 3. So we can very easily put this expression in for y without having to do any work beforehand. So we've got 2x plus 2, and then instead of y, put negative 2x plus 3 equals 4. So just that entire first equation, just like it was originally, instead of y, we put negative 2x plus 3. And now, once again, we have to solve it, so we'll distribute this 2. So 2x minus 4x plus 6 equals 4. And so we'll combine some like terms and subtract 6 at the same time. So negative 2x equals negative 2. And so when you divide by negative 2, you get 1. Just like before, we'll take this equation already solved for y equals negative 2, but instead of x, we'll put 1 plus 3. And now we can solve this. So y equals negative 2 plus 3, which equals 1. So our solution there is the point 1, 1. And our last example here. This time we have an expression set equal to x. That's okay. Just make sure when you substitute, you put it in for the correct variable. We're going to replace x here this time because it's x equals 3y minus 2. So 6y minus 2, and then instead of x, we put 3y minus 2, and this is set equal to 4. So let's solve this. We'll distribute this negative 2, so 6y minus 6y plus 4 equals 4. Now kind of an interesting thing happens here. If we just go ahead and combine like terms, this goes to 0, right? 6y minus 6y is 0. So what we end up with is 4 equals 4. And if you subtract 4 from both sides, you get 0 equals 0. So essentially the same thing. And when this happens, this means that no matter what y was, whatever number we put in for y here, we're always going to get 4 equals 4. The equation is always going to be balanced. And what this means is that we have infinitely many solutions. And if we look at the equations, what this actually means is that these are the same equation. If we solve that top equation for x, we would get x equals 3y minus 2. And so this means, if you remember from our graphing notes, that these two lines are the same. If we graphed these, they would be in exactly the same place on the graph. And so every point they share, every point they have is a point that they share. And they have infinite solutions. Okay, so that's substitution. It's in the name. You have an expression or a number, as we saw in the first one, equal to one of your variables, and then you can just substitute that value in to the other equation and solve. Now let's take a look at elimination. So this is usually the preferred method if you don't have an equation already solved for x or y. You're going to use elimination. So what you're looking for with your equations, first of all, is that they are lined up. So we have x's lined up, you got your y's lined up, and then your constants on the other side of the equal sign lined up. That's the first thing you want to look for. And the second is you want to look for opposites on your coefficients. So if you look at x's here, we got 4 and negative 2. Those are not opposites. But here we have a positive 1 and a negative 1, and those are opposites. And so this system is ready to go for elimination. What we can do is just add these together. And so 4x plus negative 2x is 2x. 1y plus negative 1y is 0. Those cancel out, which is why we want opposites in the first place. And this is set equal to then 4. And this is a really easy equation to solve. Divide by 2, and x equals 2. So we already have half the answer. And now we do have to do a little bit of substituting. So we know that x is equal to 2. We can take either one of these first equations. I'll use the first one. And then put 2 in for x. So 4 times 2 plus 1y equals 10. And now I can solve for y, because 8 plus y equals 10. So just subtract 8, and y equals 2. So my solution is the point 2, 2. So elimination can be a little faster depending on your system, depending on the equation you get afterwards. Now, for example, f, you can see we don't have opposites right now. We've got negative 3 and 1 on the x's. We've got 1 and 4 on the y's. And so this could be an equation that you decide to use substitution with. You'd have to solve either of those equations for x or y. But we can also use elimination by multiplying one of our equations to match up. I'm going to go ahead and multiply the second equation by 3. And I think you will see why in a moment. So the first equation doesn't change. It's still negative 3x plus y equals 1. Our second equation becomes 3x plus 12y equals 12. And now we can eliminate because we have opposites on the x's. Negative 3 and 3 will add to 0. So those cross out. We get 13y equals 13, so y equals 1. And now again, take either one of those first equations. The first one seems easier to me. Negative 3x plus y is equal to 1 equals 1. Right, so instead of y, I put 1. And now I can just solve that equation. Subtract 1, we get negative 3x equals 0. And so x equals 0. So our solution is the point 0, 1. So if you don't have opposites on your equations, you will have to multiply one or potentially both by some number to get there to be a pair of opposites that when you add, they cancel out. Looking at example G, 4x minus 2y equals 6 and 7x minus 5y equals 0. Well, we don't have opposites. 4 and 7, negative 2, negative 5, those aren't opposites, but I can get them to be. So looking at the y's, I think, is what I want to do. You could also look at x, but for the y's, I'm going to go ahead and multiply this top one by 5 and this bottom one by negative 2. And that's going to give me a 10 and a negative 10 on my y terms. So let's see how that worked out. So 20x minus 10y equals 30, and negative 14x plus 10y equals 0. And that worked nicely because now when I add these together, the y's will cancel out. So 6x equals 30. When I divide that, x equals 5. So sometimes you have to multiply both equations by some number, but that is okay, as long as you can look and see, what do I need to do here? What numbers should I multiply by? And make sure, like I use the negative 2, make sure you get a positive and a negative at the end. So if they're both the same sign like these were, one of your numbers should be negative. I also could have multiplied by 7 and negative 4 to make my x's 28 and negative 28, but I chose to do y. It's really up to you. Let's put in 5 for x here. 4 times 5 minus 2y equals 6, just using that first equation. And so 20 minus 2y equals 6. So to solve this, subtract 20, just a two-step equation. Negative 2y equals negative 14, and so y equals 7. And my solution is the point 5, 7. So on paper, it looks like a little bit more work sometimes, but a lot of it's just rewriting or then solving the equation. As long as you understand what's going on here, should be okay. Now on the next one, again, we don't have opposites, but I think I can just multiply the bottom equation. I'll go ahead and multiply it by 2, and that'll give me a 2 and a negative 2 on my x's. So let's see what that looks like here. So 2x minus 6y equals negative 14. That didn't change. And my second equation will be negative 2x plus 6y equals 12. All right, and now we can add these together to cancel out those x's, but something else interesting is going to happen here. The x's cancel out, and the y's cancel out. Negative 6 plus 6 is also 0, so I've got 0 equals negative 2. And this is obviously not a true statement. 0 does not equal negative 2. And so when you get something like this, where your variables all cancel out, and what you're left with is not a true statement. Something equals something else, and you can't change it because there are no variables left. What this means is that you have no solution. And if we solved these equations for y, we would get two equations with the same slope, but a different y-intercept. So thinking back from the graphing notes, these would be parallel lines. And so this is what happens. The x and y variables cancel out. You still have some number over here that does not cancel. And so you end up with this equation that can't work. So this is no solution. Okay, so that's the gist of substitution and elimination. Kind of in the name, substitution, you're taking an expression or number that's already equal to y or x or one of your variables, and you're substituting it into the other equation. And for elimination, you're trying to organize and rearrange your equation so that two of your coefficients that are opposites will cancel out when you add those equations together. And then you do have to do a little bit of substitution at the end. So let's think about our three methods that we've learned: graphing, substitution, and elimination, and look at some systems and decide which method is the best and why. So the first one here, example I, says x equals 3y and 10y minus 5x equals negative 10. And now for this one, I would use substitution. Because of the first equation right here that says x equals 3y, this is already solved for x. So it would be pretty simple to just take that 3y and substitute it in right there for x. For the second one, y equals 2/3 x plus 1, and y equals 2x minus 3. Now for this system, I would use graphing, as long as I had a graph to use. And the reason is because these are both in slope-intercept form. And with the fraction here, I don't really like the idea of using that in an algebraic method like substitution or elimination, because I'm going to have to deal with that fraction. But graphing is pretty simple. So I could even just draw myself a graph and try to use that. So because they're both in slope-intercept form, I would use graphing. And so for the last one, 3x minus 4y equals negative 1, and 2x plus y equals 3. For me, I think I would use elimination. And mainly because both of these equations are in what's called standard form, which is ax plus by equals c, where you've got your x's and your y's together on one side of the equation and some constant on the other. And that's really easy to use elimination with because they're already lined up. And all you have to do here is multiply that second equation by 4. And that would let me eliminate. But I could see an argument for substitution if you wanted to solve that second equation for y. That could work as well, but I think elimination is the easier way to go here.